Welcome back. After learning something about the interpolation methods and regression, in this lecture we shall be taking some examples of interpolation, and we shall see where all we need this kind of methods. I will be giving you just two examples to illustrate how we can use the interpolations. So here we have a problem which is very much encountered in our balance equation solution, in that we find that many times we are required to find some kind of properties like density or thermal conductivity, specific heat, enthalpy, entropy, internal energy, etc. And then we have to resort to either some graphical way of representation of those data or some tabular data are given to us. And many times we find that the temperature, pressure at which we want to determine or estimate the property values are not directly given in the table. In those cases, we have to have some kind of interpolation methods which will be able to give us the values of the required property at those intermediate points. Okay. So, in this problem, we have to determine the enthalpy of superheated propane vapor at 0 degree centigrade and 0.05 bar from the given thermodynamic chart. And we have to also compare the percentage errors for different types of methods, whatever we have learned so far. Now, you see that whenever you are about to go for interpolation, it becomes a very critical in judging that which kind of interpolation formula you should use. Generally, we want to keep the interpolation very simple, and in most of the cases we go for the linear interpolation whenever we are having a small range to consider. But many times we also find that whenever some of the property values are given at very sparse way, okay, in those cases we have to be very careful to figure out that whether we can go for linear or we have to go for some kind of non-linear interpolation methods. Okay. Now, with this in mind, first let us see that we are given this kind of data to us. So, here you see that the properties are like this, that first column is telling us the temperature in degree centigrade, and then we have the specific volume, that is small v, then we have the internal energy, then the enthalpy, and then the entropy, and all these things are given for some specific pressure. So, pressure is given both in bar as well as in megapascal, and here it is mentioned that at this particular pressure the saturated pressure temperature is this value. All this is the boiling point. Now, you can see in this particular table, like the first is sat, that means this is T sat corresponding to minus 93.28 degrees centigrade. Now, because we are talking about superheated propane vapor, that means we have to consider all the temperatures which are above T sat. So, that is why you find that in this particular table we have the temperatures which are more than the T sat of the particular material at the given pressure. So, this kind of chart you will get for different types of components. So, we have been asked to find out that at 0.05 bar and at 0 degrees centigrade what is the enthalpy. Now, you see that in this particular table the values of enthalpy are given, but for sake of finding out the percentage error by considering different types of interpolation methods, what we are doing is this: we shall be using some interpolation method and try to estimate the value of the enthalpy at this temperature, and whatever value is given to us here, okay, this value will be our standard value with which we shall be comparing the estimated value from the interpolation formulae, and from there we can figure out that how good or how bad is our interpolation formula. Okay. So, let us go ahead. So, here we are using the Newton's divided difference linear interpolation, that is the easiest we can think of, and as earlier we see that this is the particular formula we use. So, here it will be HT. This will be H only. So, this HT we have to find out in terms of some other enthalpy values at some other temperatures like T0 and T1. Okay, so this is the formula. So, here the T is 0 degree centigrade and the P is 0.05 bar. Okay, and from the tables we find the true value as 488.2 kilojoule per kg. Now, first what we do, we go to estimate, we just first assume that the limits like minus 80 degree centigrade and 20 degree centigrade. That means, here we choose this 20 degree centigrade and minus 80 degree centigrade to arrive at a value for this 0 degree centigrade enthalpy value. Okay, let us see what happens. That means, if we suddenly take a very large range to make the interpolation. So, as I told you in my earlier lecture, that range of interpolation has to be chosen carefully depending on the linearity or nonlinearity of the particular problem. So, sometimes we can figure it out from our physics of the problem, and sometimes we may not be able to figure it out from the physics of the problem. Then we have to have this kind of data chart with us to do those things. So, we shall see these things one by one. So, considering these two temperatures and then figuring out that enthalpy values at these two temperatures, we do the iteration and find that this is the value of the enthalpy we are getting. And what we find that from the true value, if you look at, we find that we are getting a very small percentage error, that is about 0.68%. Now, you can see that at the very first go, even after considering a very large range of temperature, we have been able to get a percentage error very, very small. It is less than 1%. That means, we are able to get a very good estimate of the enthalpy or the particular property. Now, this should trigger us that why it happened. It could only happen if we find that we have a very linear relationship. In that case, what we find that slope will be constant, so that whatever range we choose, we are going to arrive at a very good estimate value. So, to understand this, what we do, we just simply plot it. We plot this data whichever is given to us at 0.05 bar, and these are these black color things are the actual values which are given in the table. And then what we do, we first fit a linear curve. Here we have fitted the linear curve, and this can be fitted using some package like Origin, like Excel. You can use any of these packages or MATLAB, and if you fit them, it will also give you the correlation coefficient, how much you are getting, and here you can find that R square error coming to be 0.99799. Now, this particular value tells us that this is a very good fit even with a linear thing. That means, if it is as near as unity, we take the fit to be very good. So, we are already getting a very good fit, okay, with a linear fit within this particular zone. Okay, and that is the reason we are finding that even if we are choosing a very large range of the temperatures to estimate the value, we are able to get a very good percentage error, very less percentage error. And just for sake of testing, we can also fit one polynomial fit. Okay, here we have taken a quadratic fit. Okay, and here we see this particular line is giving us the quadratic fit, and here we find that the R square value has come to 1. So, there is little difference between this 0.99799 and 1. So, in order to reduce our computation time, we can just go with the linear fit without going for this. Okay. So, that is what we are finding, that there is no extra gain we are getting by increasing the degree of the polynomial for getting the interpolated value. Okay. So, whenever you are doing this kind of interpolation, either you try out with the linear interpolation if you find the range is quite small around the particular independent variable value. Okay. If the range is large, only then perhaps you can think of going for a nonlinear interpolation, but it is always good to check that by this graphical way, that how this linearity or whether the things are linear or not. Okay. So, that will reduce your time of iterations. Now, we have taken a case 2, and in this what we are doing, that we have just reduced the range. Okay. So, earlier it was 80 degree centigrade, minus 80 and 20 degree centigrade, now it is minus 10, 10 degree centigrade. Now, here we find that we are getting this value 0.05%. Now, whether we should go for 0.05% or whether we can stay with 0.68%, that will again depend on the problem. Okay. Now, it is not necessary for you always to keep reducing the percentage error. Many a times for engineering analysis, we are quite used to having errors like 1%, 2%, even 5% errors are permissible at times. Okay, so it is not always very necessary for us to keep on increasing the degree of the polynomial or keep reducing the range of the estimation and trying to reduce the percentage error. It will all depend on the case by case basis whether we need to reduce or not, but in this case what we find that 0.68% may be taken to be a good value. Next we go to Lagrange interpolation. Now this formula is different as we have seen earlier, and in this case we are again going to perform a linear interpolation with the Lagrange polynomial. Now here you see that we have taken, as you know that in case of Lagrange we have to take these three things. So we have arbitrarily chosen these three temperatures, minus 80, minus 20 degrees centigrade and plus 20 degrees centigrade, and at these temperatures from this particular table we find the values of the enthalpies. And now we put the Lagrange formula. This is a linear interpolation formula of Lagrange, and we find that we are getting again a value which is about 0.65% having error. So you see that whether we are using the Newton's linear interpolation or Lagrange linear interpolation, in both the cases we are finding that we are having almost the same percentage error. Okay? Only now difference is this: in case of Newton's formula we needed only 2 points, whereas in case of Lagrange we are going for 3 points. Okay? Now without doing any more of these deductions, what I have done is this: I have calculated separately using different interpolation formula this percentage error for this particular problem. And here you can see we have tabulated them like Newton's linear, then quadratic, Newton's quadratic, Newton's cubic, then Lagrange interpolation first order, Lagrange interpolation second order, and here you can see all the percentage errors. So what we are finding that, for example, you take Newton's interpolation methods, we are finding that as we are increasing the order of the interpolation, we are able to decrease the percentage error. Okay? But at the same time it is coming at the cost of the computation effort. Okay? At the same time that even for Lagrange we find that if you go for second order, it is giving us a less percent error than for the first order. Okay? So this way we figure out that increasing the order of the interpolation we are able to get a better and better estimate. Again, as I said, that we should not get tempted by these small percentage error. We should be very, very clear in our mind that whatever is the requirement for the particular problem, accordingly we should go for the interpolation method. Now let us go to another problem. Now in this problem the thing is this, that we are now going to deal with two independent variables at which we have to interpolate. Now earlier problem we found that we were interpolating only with respect to the temperature. In this case we have to interpolate with respect to both temperature and pressure. So here the problem is that we have to find the enthalpy of superheated propane vapor at minus 5 degrees centigrade and 0.07 bar. Now here you can see that this minus 5 degrees centigrade does not exist in this temperature, and this 0.07 bar is also not there. So it is 0.05 bar and 0.1 bar. That means what? That the enthalpy has to be interpolated once with respect to the temperature and then with respect to the pressure. Okay? So here you can see that since both the given temperature and pressure at which the enthalpy has to be determined do not match with those given in the chart, interpolations with respect to both temperature and pressure have to be done sequentially. Now point is this: what sequence we should adopt, whether we should first go with the temperature interpolation and then pressure interpolation, or first pressure interpolation then temperature interpolation. Now this can be arbitrarily done, and we shall see that it really does not matter that which sequence you follow. So that we can say that in method 1 may be that we interpolate with respect to temperature first at two pressures bounding the given pressure, and then we interpolate with respect to pressure at the given temperature. What it means is this: suppose what we do, that we go to the temple. Okay. Now, first we interpolate with respect to temperature. That means what? That we have 0 and minus 10. So, we get the value at minus 5 degree centigrade at 0.05 bar. Similarly, we can get the value of enthalpy at minus 5 degree centigrade at 0.1 bar by interpolation. Now, with these two values, we again interpolate to get the value of the enthalpy at from 0 at 0.07 bar and at minus 5 degree centigrade. So, this is method 1. Okay. And in the method 2, what we are saying, that interpolate with respect to pressure at two temperatures bounding the given temperature, and then interpolate with respect to temperature at the given pressure. That means what we are doing, that first with respect to the, that means you find the value at 0.07 bar first, and then at minus 10 degree centigrade and 0 degree centigrade, and then what you do with these two values, you find the value of the enthalpy at minus 5 degrees centigrade and 0.07 bar. So, let us see these two. So, here we have we adopt arbitrarily again our Newton's divided difference linear interpolation, and this is the interpolation formula. So, in the method 1, what we do, that let us take the P0 to be 0.05 bar, and let us choose the temperatures as 0 degree centigrade and minus 10 degree centigrade. So, here are the enthalpy values at these two temperatures and at this particular pressure. Now, what we do, we find the that given temperature is minus 5 degree centigrade. So, at this temperature, at this P0 pressure, we find the value of the enthalpy from the Newton's linear interpolation formula. Next, what we do, we choose the next pressure, that is P1, that is 0.1 bar, because this pressure is bounding the given pressure of 0.07 bar. So, again at this pressure we take the two temperatures 0 degree centigrade and minus 10 degree centigrade, and we get the enthalpies, and we again get the value of the enthalpy at minus 5 degree centigrade. Okay. And with this value and this value, what we now do, we again interpolate with respect to pressure, and we get the value of the enthalpy like this. Now, you see that there could be some questions like, do we need to really stick to this same range for this pressure and this pressure? Well, perhaps it is advisable to stick to same range, assuming that the behavior of the variation of the enthalpy with respect to temperature should be maintained in both the at both the pressures. It might so happen with some properties that you may find that this linearity may be destroyed if you go for some other value of the pressure. Okay. So, it is better to stick to the same range, but there is no hard and fast rule mathematically to go with the same range of these bounding values. Now, what we do, we adopt the second method. In the second method, what we do, we first choose the one limit, that is minus 10 degree centigrade, and at this temperature for 0.05 bar and 0.1 bar, we read out the values of the enthalpies. Now, with these two values of the enthalpies, what we now do, we find out the value of the enthalpy at this particular pressure, that is 0.07 bar. Okay. So, this is after getting this 0.07 bar, we are getting this enthalpy value. Now, what we do, we go for the 0 degree centigrade, and again we adopt the same method, and we get the value of the enthalpy at this 0.07 bar at 0 degree centigrade. Now, with these two values, we now interpolate with respect to temperature to get the value of the enthalpy at minus 5 degree centigrade. Now, you can see that this particular value, which is the value we wanted to have, this value and this value are almost the same. So, what we conclude from here? We conclude that these two methods give the same enthalpy after interpolation, and the solution is independent of the order of interpolation. That means, the sequence which whatever sequence you might maintain, whether first temperature then pressure or first pressure then temperature, it really does not matter, and we are going to have the same interpolated value. So, these are some of the references which will give you some more detail about the methods we have talked about. Thank you.